Okay, so from now on, we will be using Zoom for our synchronous meetings. The Google Meet is wala na siya kuan, wala na siya recording dito. So we'll be using Zoom, and we'll having our synchronous class every Tuesday 4:30. So thankfully 4:30 na ang inyong klase na kayo sa'yo. And so I'll be sharing with you the syllabus. So I have updated the syllabus. Makita ninyo? What are you seeing? Can you see the Word file? Hello?
Yes, ma'am.
Okay, so again, this 131 is a continuation of the 130 basic organic chemistry course. No, this is only offered for the BS chemistry students, of course. And the prerequisite or prerequisite. The prerequisite is Chem 130. So if you don't pass the Chem 130, you can go up with 131. So I have updated the syllabus. Now the syllabus for 130 131 in the previous semester is very, very long. So I have slashed some of the topics which cannot be covered. No, and I will be slashing again some chapters kay dili makaya until the final exam, which is June 9 to 15. Hopefully the academic calendar or the registrar wouldn't be, or there is a possibility that they move, but at least now they published already the academic calendar. So I'll be posting this in the LMS. And you have an academic break April 11 to 20, and the tentative exam is on April 7 to 13. Hopefully we can cover chapters. So we'll continue chapters. If you remember, we didn't finish the chapter 6. So we'll continue, and I have sent the link for the first 3 chapters of the chapter 6. The first 3 subtopics of chapter 6, you can check on the LMS. And then we will continue, start to chapter 6, and then it's a continuation to 7. And it's a very long topic. So what will happen is I have slashed a lot of topics so we can cover. And the remainder of the topic that cannot be covered, you will take that in the advanced organic chemistry course. I think it is an elective. It should be, I'm not sure what will be offered, but I know that CERTEM will be offering the advanced organic chemistry and some other electives. No? So you will be, that will be useful no, for your exam. Again, I mean your exam, board exam. Okay, and so this course is 5 units again, and 3-2 will have our laboratory activity, but we had a meeting last week, I think, and since we couldn't do full-time face-to-face class, and hopefully from your end you can request if you can do some laboratory activities. They are talking about opening or welcoming the face-to-face classes, no, but the full, I think that it will still be on the next semester, the first semester of the 22 to 23 academic year. But if we can request for that, hopefully that the university will allow. Now, there are guidelines na the issues that shed for that. So what else? So for the meantime, if we couldn't, there will be some activities na that we couldn't do, or if they don't allow. So what we do is, of course, I will just be showing you some video of the laboratory activity, and we'll talk about that during sa inyong laboratory time. And so there will be a lot of laboratory techniques that will be used and in support for the reactions that you'll be using. in the lecture. So I've noticed that a lot of you complained last time for the exam, no? So you will have to train yourself when we do the exam. It's always time limited, and you should practice before you dig into the examination. No, so you should practice, make sure that you submit your problem sets, and when you do your problem sets, you do practice. So for you to practice, I send in the reference material, there is since our main reference is Solomon's, you can click here. I have included the study solutions manuals. Okay, study guide solutions manual to accompany your organic chemistry courses. No, so you can, for example, there's a problem set in the chapter. This one for our main textbook. I think this is the one. No? Then you can go to the solutions manual if you want to really take time to solve some problems that you couldn't answer sa itong main textbook. And so there are solutions in there you can study if you really want to improve your organic reactions. And I have noticed that even for those students who did retake or removal exam, no, or even if you did a removal exam for your classes, you weren't able to improve, they weren't able to improve their grades. So what we will do, maybe next week when you have time, I will export all the exams that you took last time, and then I would like you to perfect the exam. To take the exam again sa to midterm and finals, and so you can train yourself sa pressure now when you take the exam. It's time limited, and of course you always have to recall it's always connected. And when I say reactions, we'll be doing reactions this way. You will have reactions. I think in 130 we did the mechanisms, right? So we did some theoretical mechanism reactions, and you always train yourself to do reactions where the electrons go, the arrows from. So some of you get confused on how to do that. So you have to practice, do the reactions, do the arrows, where you should always ask where do the electrons go. Okay, and so that's why I have sent to you the solutions manual. And of course, for the exams, I won't be taking some of the questions from the solutions manual that you can study, but who knows if I get some of the questions from the solutions manual. So you can study if you really want to perfect your organic chemistry course. What else? Okay, so if you have questions, so how many chapters here? So I still couldn't, I'm trying to budget the time that we have so we can cover as much chapter as possible. So I will update this one and I will upload this for the next meeting because I will slash some of the chapters. Yet, and again, as I mentioned, whatever chapter that can't be included for our class, then I will request that to be added to the Chem 132 advanced topic reactions. There will be probably 4 chapters can be exported or can be discussed, tackled to the higher chemistry course, advanced organic chemistry, and there will be a lot of reactions involved. Okay, so we will continue with our lesson, and as I mentioned, we'll continue with chapter 6. If you forgot about the chapter 6, no, first few topic, so you can review the video, and then we'll continue with the discussion. Okay, so chapter 6 is all about ionic reactions. If you remember your chapter 6, and it's all about the nucleophilic substitution reaction and the elimination reaction. So far what we have discussed in the last chapter, since it's a continuation, it's about the nucleophilic substitution. And so we talk about usual substrate. We have the alkyl halides, but it's also possible whenever you have a heteroatom attached to your carbonyl carbon, like alcohol, for instance. So in the next chapters, we'll be talking per functional groups and the reactions per class of organic compounds. So you just have to remember that in nucleophilic substitutions, now we always have this nucleophile, a nucleophile, which is an electron rich. There's always an electron here. And since there's an electron, it's considered to be a Lewis base. No? So if you remember what is a Lewis base, it is the reagent that donates electron, okay, to another substance. And then in the nucleophilic substitution, since it is a substitution, there is a living group. So this is the living group. This is the one that's being substituted in the nucleophilic reaction. So the living group leaves, and then you have the nucleophile in it. And the living group is 3. And then when you look at the overall reaction, you always have to remember on the total charge of the system. So you added the charge of the system on the left and on the right. For example, here there is a total net negative charge on the left. So all the reagents or the reactants. So you always have to consider that also when you do reaction mechanisms or when you do reactions para dili mo mawala. Okay, so here we have an example of the nucleophilic substitutions. For example, you have electrons here. You always have to look for the electrons, even if when the reaction is written without electron pairs or lone pairs in it. For example, you have OH, no? They always have to remember that those are heteroatoms. So the halogens, the group 6, no, there's always electrons in there. So, and then you will have to consider always in the carbon, which one would have partially positive. So for example, here you have an electron, and you will have to consider which part of this will the reaction happen. So whenever you have an electron, the atom can either be fully negative or partially negative. So it's always where's the partially negative end, where's the partially positive end, because that will where the reaction will happen. So in this case, for example, your carbon here is attached to iodide ion, and of course your iodine here would bear the partial negative charge. And
Nagklase yung amo teacher. Amo teacher.
Can you mute? Wala mo siya nakamute. Kinsa man eh.
So good naman ang klase ko man a week. Pero sa next week ang face to face. Next week gani. Kuman nagsugod ang klase.
Kinsa man to? Can you please mute if you're talking? Okay, so again, when you have your substrate here, we call this one as a substrate. You always have to look which part would be partially positive, which part would be partially negative. For example, here there is an electron here, and there's an electron pair here. You don't expect that this one will attack this one, right? So this one, there will always be repulsion from electrons and electrons. Of course, you expect that this will attack the partially positive carbon. This one becomes your later. Now there are 2 types. Now this is the end where you have partially positive, but if this one leaves first, this become a carbocation. Okay, so you just have to remember, go back again to the mechanisms, usual mechanisms. Where would the arrow go? And you always have to ask yourselves, because in the next chapters of this course note, some of the structures can get very, very complex and very, very complicated. So if you don't understand this basic reactions, then it will get it'll be harder for you to understand. No, you always just have to ask which one is the negative end, which one is the positive end, no, or partially positive end, partial negative end. Whenever there is an electron, okay, always remember on the partial negative end, the partial positive end. That's where the reaction happens. Okay. So here in the nucleophilic substitution, again, it's a heterolytic bond cleavage, no? And what do you mean by heterolytic? When the atom leaves, no, it takes with it all the electrons in the bond. So for example, the carbon and iodide bond, there's covalent bond here, all the electron would go to iodine. Okay, in the homolytic bond cleavage, tunga siya homo, there's only one electron being carried. So this is not the case for nucleophilic substitution. For that kind of homolytic bond cleavage, we'll be talking about radical reactions, so that will be on the next chapters. Okay, so for okay, so the question is, when you have a nucleophile and it attacks your carbocation or positively charged carbon atom, no? The question is, where does the bond between the leaving group and the carbon break? When does the bond between the leaving group and the carbon break, or does it break same time? Okay, so here we've learned in the SN2 reaction that when the what did we learn with the SN2 reaction? That again, we have to remember that a nucleophile is a reagent that always seeks a positive center. So of course, your nucleophile is a substance that contains or that pairs electrons or that pairs a negative charge, okay? And therefore, it will always seek a positive center. So whether the carbon is partially positive or fully positive, it will always seek a positive center. Now, the question is, kanas aman will be ang atong living group? Is it simultaneous or would it leave first before the nucleophile attack? So that will be the question we will encounter when we do the nucleophilic substitution reaction. Okay, so your nucleophile can be a negative charge nucleophile like your hydroxide, of course. So your source of this is, for example, sodium hydroxide. No, that's an ionic substance. You expect your hydroxide to be negative charge, or it's a neutral nucleophile, for example, your water. No, but you see here that there is an electron. So because there is an electron, then there is a possibility that it can attack a positive center. A carbon that is positively charged, whether partially positive or fully positive. So this is an example of a neutral nucleophile. What else? Another example of a neutral nucleophile is an ammonia. Okay, you have NNH here, but you always have to remember, even if, for example, it's not written this way, that like all the electrons are being shown, you always have to remember group 5, nitrogen, oxygen, chlorine, all in the group 7, there's always a lone pair. Of course, as always, they follow the octet rule 2468, and there's a lone pair here. So this is an example of a neutral nucleophile. So it can attack a center or carbon that is positive, whether partially positive again or fully positive. So these are some of the questions that arise or that was given during the exam, and it saddens me to see that some of the students couldn't even identify which center is positive, which center is not. So for example, here, this is the one that is, here you have a sulfur that has an electron pair, so expect this one to be a nucleophile. Usually your nucleophile is paired with a positive ion. Okay, that will be your source. So your nucleophile again can be, if it's negative charge, it's paired with a positive ion. So here, this is your substrate and this is your leaving group. Okay, and so of course this one will attack the positively charged carbon here. Why would become positively charged? Because your iodine is more electronegative than carbon, so it will bear partial negative charge, and this carbon will become partially positive charge. So you will just have to find an arrow, okay, and then form a bond. So in this, you will use the electrons in this nucleophile. When the nucleophile attacks positive centers, it will always use its electron pair. Okay, so it will use its electron pair to form a bond. For example, sulfur here will use its one lone pair to form a bond with carbon. And when it forms a bond with carbon, the bond between carbon and iodine will be broken. So as man paingon, it will go to the iodine. So it's 246 plus the ion here will become negatively charged. Excuse me. I don't know where's the mute. Okay, so back to the discussion. So again, I have mentioned earlier, can you please, that will be part of the exercise. I would like you to perfect the Chem 130 exams. No, that means if you were able to perfect the exams, you were able to correct the mistakes. Now, I remember before when I did take the chemistry board exam, no? And then, of course, sa review pa lang daan, you will have an idea whether you will pass you'll get the high score or not. So I remember when I did the exam or the review, during the review, no, I had a lot of mistakes, for instance, no, and then I retake the set of exams again. And then if I couldn't improve my score, it only means that I wasn't able to correct katong mga sayop nako. Okay. So if you weren't able to correct that one, it will really propagate within you. You couldn't remember anong nasayop ta, where did you get wrong? So you always have to find those part or those sections na you will have to correct yourself, no, para ma-perfect ninyo. Okay, so that's a good indicator that you learned from your mistakes. You learn to improve on how to improve your understanding sa course or sa, let's say, organic chemistry. Okay, so here again, this is just an example. Here you have again your substrate here, and this is your leaving group. This is your nucleophile. So you have an electron pair. You always have to find there is an electron pair here. So there most probably this one will attack carbon here, which is partially positive. Nga naman partially positive niya siya because it's connected to iodine, and iodine is partially negative here. It crosses the electron swing. So yeah, you expect your carbon here to be partially positive. So this carbon is partially positive, and you have a nucleophile here, an electron-rich reagent, okay, a Lewis base. So it will attack this positively charged carbon atom, partially positive charged carbon atom. So since this nucleophile has an electron pair, it will use its electron pair to form a bond. So you have carbon, bond CH3, you have this, and then the bond here will go to iodine, okay? So, or the bond here, 246, and then we will have 2468, and of course, then it will bear a negative charge. So you notice on the total charge on the left side and on the right side, for all the reagents and reactants on the left side, you notice that there is a total 0 net charge, okay? Because you have here, for example, because we included here the counter ion for this nucleophile. Counter ion gani kato yung pair niya nga positive ion. Okay, so if you include that one, then you expect on the product side neutral po siya. If in the reactant side you don't include the counter ion, for example, S dot nang siya negative, of course in the reaction you don't include na the sodium here, and you expect that the total charge would be negative. Okay, so by the way, anong gamay raman mo? I always ask myself, pila gani mo karon? 12. So there are 3 who is absent. By the way, you can go to the LMS and indicate your attendance. And for the grading sheet, if I can remember your grading sheet, it's grading sheet. Anyway, later na. So it's the same thing. There's a problem set. How much is the problem set? Stop sharing. Anyway, there's a certain fraction for your problem sets. If I don't give a quiz, you just submit all your problem sets and answer it, and there's a great chance that you will get a higher grade. No, you submit all your problem sets. So share. Okay, wala nakabutang. So the grading sheet here, or for the grading system, 60-40, 40% for your laboratory and 60% for your lecture. So you should submit all the laboratory activities. What else? And for 60% of your lecture, how much is I think 30% is your exam. 30%, around 30% is your 30% of your grades a lecture would come from the problem sets and quizzes, assignments, or attendance, or attendance will go to participation. Okay, I think that's all. So let's go back to the saan ako? Okay, so here back to the examples of ionic equations. So it's a unique because you have your nucleophile and can be, your nucleophile can have a charge or can be neutral. Okay, again, so here is another example. You have a nucleophile here, there's an electron pair and there is a substrate here. You expect this one to attack the part here which is partially positive. So you look for which part of this whole structure will be positive. So if this carbon is connected to group 7, so this is more electronegative than carbon, of course, expect this carbon to be partially positive. So this NH3 would form a bond with this one. Okay, so NH3, and then you will have your CH2, this is CH2, NH3, and then NH3, since there is 4 bond, then it will become positive. Okay, and then Br here minus. So what happens when you have your NH4? So NH3 will attack again. Okay, let's see. So once it attack, it's connected. Okay, so for example here, it will attack this one, will be partially positive. This carbon here will be partially positive, and bromine, of course, partially negative, positive. And this is partially negative. So the lone pair, we use that one to form a bond with carbon here. So what will happen? You have your CH3, okay, CH3, CH2, and then CH2, and then it will form NH, diba NH3 man na, it will form NH3, NH3. And since the nitrogen will have four bonds, okay, nitrogen will have a positive charge here. Okay, to eliminate that one, so matingala mo asa na ato ang NH3. We will have hydrogen, hydrogen, okay. So there is a positive charge on nitrogen here. So there is another reaction. This is an excess. So an excess of that, an excess of NH3. You have a dot here, the lone pair from nitrogen, and we will use that one to attack the positive. This is the hydrogen here is bare, it's positive charge. Nitrogen is more electronegative, so it would have more tendency to draw the electrons to nitrogen kaysa kang hydrogen. So it will attack the hydrogen, and then the lone pair will go back to nitrogen. So what will happen? We will have what will happen? We will have another further reaction, which is kanina siya. Ma-remove ang you will have CH3, CH2, CH2. Ma-remove, there is an arrow here. The bond here will go okay, the bond will go to nitrogen, so we'll have N hydrogen bond, hydrogen, and a lone pair. Okay, a lone pair. Plus N H. Kuha man siya sa isang hydrogen, it will become 4 hydrogen plus. Okay, it will become positively charged for nitrogen. You always have to remember on the valency for every group of atoms. For example, nitrogen, for nitrogen group 5, they will always just have 3 bonds and a lone pair, no? To be neutral. Pag 4 bonds na, to become passively charged. You always have to remember on how to get on the formal charge. Okay, so NH4, and then of course Br here, it's being released. So dili mo matarantar, no, whenever it seems like or unsa na na siyang reaction, you just have to follow on where the electron goes. Okay, else. So this is our nucleophile substrate and the living group, nucleophile substrate, and the living group, nucleophile substrate, of course, and the living group. So living groups is a substrate that can leave us a relatively stable, weakly basic molecule or ion. So that's a good living group is always the one that is stable, no, even if it's an ion. So some living groups would depart as a neutral molecule. For example, here, CH3OH. Balik-balik naman ko. So I already discussed this one last time. I think. CH3O. So it will attack, of course, when it attacks this one here. So you always have to ask which part is partially positive, which part is partially negative. Okay. Pareha raman ni siya sa H3OH. So this one, of course, expect to be partially positive. So dili lang ta matarantar, no? Whenever like, asa naman na paingon, you always just to look where is the electrons. So you expect the electrons to be on oxygen, nitrogen, fluorine, bromine, group 7. Here. So this one is a neutral nucleophile. So since there is an electron, you consider this one to be a nucleophile. So it will attack the carbon that is partially positive. Nga na partially positive ni si carbon here because it's connected to oxygen. And we know that oxygen, even this one is positive, is an electronegative atom, so would have the tendency to draw the electrons paingon sa iyaha. Okay, so what happens here? This one is so many. So you form CH3, you have CH3O, O here. Okay, and then the OH will leave, it will take the lone pair with it paingon sa iyaha. So when the lone pair is paingon na kang water, okay, of course, water, you always have to check on the formal charge of oxygen, no, group 6. So 2 bonds and 2 lone pairs, that's for all group 6. So wala siya charge. Pag 3 bonds na sa oxygen with a lone pair, there is a charge. So always remember how to get the formal charge of each atom. If you can't remember, it's always group number minus number of bonds. For example, here, oxygen group number is 6 minus number of bonds 3 minus number of unshared electrons, that's 2. So 3 minus 2, that's 1, positive 1. So kung kalimot mo ana, you just have to memorize that group 6, they always have, like oxygen, always have 2 bonds and 2 lone pairs. Nitrogen always have 3 bonds and 1 lone pair. Of course, carbon always have, should always have 4 bonds, no lone pair. So here again, it will attack the carbon here, and you will have CH3O, H. So from 2 lone pairs, follow lang ninyo, gamitin ninyo, convert ninyo lone pair to a bond. Okay, to form a bond here. So isa na lang. And then si kanisha, the lone pair, since mo attack man siya diri, it forms a bond. So mabiya ni siya dapat so that carbon will retain 4 bonds. No? So the OH, the oxygen here will carry the lone pair from the bond. So it will have 2 lone pairs here. And having that structure, oxygen will be neutral, would have a charge of 0. And then since your oxygen, it forms a bond here, it will have 3 bonds from 2 bonds diri up plus another bond in the lone pair. And when you check on the formal charge of oxygen, it will be positively charged. And this is what I'm saying, that for the total group of atoms or agents on the left side, the total charge is 0 plus 1, positive 1 on the right side, positive 1 and 0 is positive. So you will know that's a double checking part for you to know that wala may nasayop na you get on the same charge before and after reaction in the system. Okay, so again here, this is your leaving group and this is your nucleophile. So let us now begin to consider the mechanisms of nucleophilic substitution. How does the nucleophile replace the leaving group? Does the reaction take place in one step or is more than one step involved? So, okay, so we'll be looking into the mechanism of yun sa paghitabo. Okay, so the first one is, I have already discussed this once. Let's see. Okay, so an example here is H3Cl and OH, now to form here, or this is our substrate, and Cl becomes our leaving group. The OH, of course, even if wala lone pair, you always have to remember oxygen has a lone pair. Maski pag sa gishow, no, wala siya lone pair, but always have to bear in mind again that there is a lone pair. No, chlorine here, there is a lone pair here, 246. No? So this will attack carbon here to form CH3OH, and Cl leaves carbon here. This happens here. Now, to know To answer this question, kinsay nauna? Niuna ba siya og attack? Nibiya ni siya or nagdungan ba siya attack? Nagdungan ba siya biya? No? So those are the questions that we will consider on the mechanism of the reaction. In this case, they found out that for that kind of reaction, when they found out that when you double the concentration of the CH3Cl, the rate of reaction also, the initial rate of reaction also doubles. And they found out that if you double, for example, what else? If you double the concentration of the CH3Cl, the rate of reaction doubles. And if you double, we look at for the same, 2 and 4. So 1 and 2, you notice here that 1 and 2, this is general chemistry 2, if you remember. General chemistry 2. If you have 1 and 2 experiment, no, so same ang initial OH, and you change initial concentration of CH3Cl, what happens is double ang rate of the reaction. The rate of reaction, the rate of which it forms this product here. So there are two ways to know the rate of reactions, right? It's the rate of the appearance of this or the rate of the disappearance of either of these reactants. Anyway, it's found out that the initial rate doubles when you double this one. And when we double this OH, so kanang parehas of concentration. Okay, let's look at 1 and 3. So same ang sa H3Cl, okay, 1 and 3, and we double the OH. So what happened is we double put ang initial rate of the reaction. So therefore, we can conclude, since pag i-double nato ni siyang CH3Cl, i-double natong OH, it will affect on the rate of reaction. And therefore, we can conclude that this type of reaction, the rate of reaction is dependent on the concentration of CH3Cl and OH. Okay, and the rate of reactions I've mentioned is dependent to both of the reagents or reactants, the nucleophile and the substrate. And the rate of reaction is directly proportional to these two reactants here, and you can have this rate proportionality constant, K, for the rate of the reaction. When you have the rate of reaction for this kind of substitution due to the two reagents, then this kind of reaction is what we call as second order overall. So when you say it's second order, and since it's a substitution reaction, there's two reagents involved. Okay, we call this one as bimolecular. And since it's second order, we call this substitution. Okay, since the OH substitute this one, and nucleophilic, since you have the nucleophile, and it's bimolecular. And we indicate 2, which means that the rate of the reaction is bimolecular. What do you mean by bimolecular? The reaction is dependent on the concentration of both the reactants, the substrate, we call this one as a substrate, the one with the leaving group, and the OH, the one that we call as a nucleophile. So again, your substrate and nucleophile both determines on the rate of the reaction. So again, we call this type of reaction as SN2 whenever the rate of the reaction involves the two species or the reagents. Now, we will look at on the mechanism of the reaction. So kinsa may nauna pag when the OH substituted the Cl, kinsay ni una? Sinibiya ba daan si Cl before ni attack si OH, or pag attack ni OH ay harapon ni biya si Cl. No, so that's the, here we've learned in the previous discussion that in this kind of reaction, in the SN2 reaction, the nucleophile will attack from the backside. For example, this is your leaving group and this is your CH3 here. It will attack from the backside of the reaction. Why would that be? Since your leaving group, like this one here, would have a lone pair, no? So it wouldn't approach near the Cl. Nga naman, there will be repulsions. It will rather, the OH would rather come approach to the substrate from the back of the Cl, no? So there is a likod to attack the carbon. So here what we call is that the nucleophile approach the carbon bearing the leaving group from the backside. And this is what we call in the SN2 reaction, there is a backside attack. No, it's not head-on, but it's a backside attack. And then what happens when it attacks on the left? So When it attacks on the left, there is what we call as an inversion of the configuration. Mabaliktad ang imuhang carbon. I had a video that was shown in the previous one. You can watch in the video. There's a video on YouTube for that. You can look into the inversion configuration now. So here, for example, here, okay, so your hydrogen here is directed dito sa left, no? But when the nucleophile attacks, kaning hydrogen will be inverted pabaliktad. So ang direction aning tulok ka hydrogen adto na sa right instead sa left when the nucleophile attacks from the back side of the substrate, backside with respect to that of the leaving group. Okay, so here in the SN2 reaction, there is a backside attack, and then there is inversion of configuration, bonding configuration. There is an animation, click on that animation. The SN2 reaction proceeds a single step without. There is no intermediate. When we do the SN2 reaction, it's a single step reaction. But what we have is a transition state. Kanang transition state, in some transition state, it's an unstable species. It's like a temporary species before the product is being formed. No? In the transition state, here, this is what we've talked about earlier. And this is your Cl, and this is H3. The OH will attack from the backside, that of the leaving group. When attacks here, what will happen is there's a transition state. It's a temporary species. It cannot even isolate this transition state. And before it forms on the product. No? So you notice that in the product, there is an inversion of the configuration. For example, here, if this is R, this becomes an S. That's how your backside mechanism for SN2 reaction. So what happens in the transition state? Now there is a simultaneous bond formation. Okay, the OH will form a bond with carbon and a simultaneous bond breaking between carbon and hydrogen. So that's how you see a broken line here. And here you see, of course, your oxygen to be partially negative. From negative, partially negative as it approaches the carbon to form a bond. And carbon will also bear partial negative charge, and it carries with it the electrons gikan diri kang carbon. Okay, to have ClCl, all the electrons will go to carbon, and the bond that's being formed, kang oxygen and carbon, would come from oxygen, and this is what we call as heterolytic. This is bond breaking is what we call as the heterolytic bond cleavage. All the electrons goes to chlorine, no, heterolytic. And so this is the mechanism for the SN2 reaction. And the transition state, as I mentioned earlier, it's a fleeting arrangement of the atoms to the nucleophile and the leaving group. And in the transition state, it involves both the nucleophile and the substrate. Since there is a simultaneous bond breaking and bond formation, no, we call the reaction to be a concerted reaction. Consort sila, no? There is it's only a single straight. When you say concerted reaction, there is a simultaneous bond formation and bond breaking that occurs, no, in the SN2 reaction. The transition state, as I mentioned, is extremely brief in existence, which lasts for about 10 seconds to 12 minutes. So here, the reaction between the hydroxide and chloromethane here to form your methanol would have a delta G of negative kilojoules per mole. Okay, so if you have here, and the delta H is negative 75 kilojoules per mole, na naman na no? And we call this one to be an exothermic reaction. And negative kilojoules, we call this one to be a reaction that proceeds with a negative free energy change. The delta G is said to be exergonic. We call this an exergonic because we have a negative free energy. Okay, the energy is released to the environment. So this one is a spontaneous kind of reaction when you have a delta G to be negative, and it's said to be exergonic. When you have a delta H to be negative, you call this one to be also an exothermic reaction, and the environment will absorb all the heat released during the reaction. So of course, from the delta G, we can calculate on the equilibrium of this reaction, this one. So delta G is equals to negative RT ln of KEQ. If you remember your phychem, or I think general chemistry tool, this one, gawas niyo siya. And you can find the equilibrium constant. So when you have a very large equilibrium constant, this means that the reaction goes to completion. So literally, this reaction doesn't go back to revert into the reactant side. So when this one, the HCl and the OH, when it reacts to form the methanol and the chloride ion, no, these two products will not react with each other to return back into this reactant, since you have a KEQ which is very, very large. So this means that the reaction goes to completion. So because the free energy change is negative, we can find the energy terms, the energy terms of the reaction to go downhill. There is a transition state here. So if this is your reactant and you have your transition state, the products, no, you will, if this is the free energy on the y-axis and the reaction coordinate, reactants to products here, this is your reaction coordinate. You will notice here that the free energy of the product is lower than the free energy of the reactant. So low value minus large value, you will get a free energy that is negative. And the delta G of the transition state delta G, we indicate with like plus here. You have a higher free energy for the transition state than your reactant. And this one is an example of an exergenic reaction. So an exergenic, when you have a negative free energy. So for an exergenic reaction, you always have to remember that the free energy of the product is much lower than the free energy of the reactants. This is for an SN2 reaction. And of course, we will see later that the reaction coordinate and the free energy level, free energy diagram for for another type of substitution reaction will be different. Okay, here is an example of another type of free energy diagram. Now, when the free energy of the product, this is NUR, okay, you have your nucleophile connected to your substrate or bonded to your substrate, and the free energy of the product is much higher than here, than your reactant. We call this one to be an endergenic kind of reaction. This is hypothetical endergenic SN2 kind of reaction. Okay, so just remember an exergenic and endergenic kind of reaction, and it's more an uphill for the transition state. You get a lot of the reactants will have to climb a lot of energy to form into the transition state, to form into your products. And so also for the temperature also will also affect on the distribution of energies at two different temperature. So the delta G, the fraction of collision, of course, will be much lower when the temperature is high here. And the delta G will just be similar, but there is a higher collision when you have a higher temperature than at a lower temperature. So there is a 10-degree increase in temperature will cause the reaction to double for any reaction taking place near the room temperature. Of course, the rate of the reaction doubles when the temperature is increased. But the delta G would still, the delta G of the transition state would still be the same. Here is an example. This is just the same. No? So the reaction, the free energy of the product is lower than the free energy of the reactants. So this is an endergenic kind of reaction. You have a negative delta G. So let's go to the stereochemistry of the substitution bimolecular reaction. Okay. So as I mentioned earlier, that when in the SN2 reaction, when the nucleophile attacks the substrate, it will attack from the backside, and there is a complete inversion of configuration. And because of that, as I mentioned in here, there's a complete inversion configuration. Like for example, in this case, when you have a cis 1-chloro-3-methyl cyclopentane, and this is your leaving group rather here, when it attacks your carbocation here, or your passively charged carbon here, so it will attack not from the side of the chlorine, no, but from the opposite side of the chlorine or the leaving group. So this is our leaving group. This is our nucleophile. This is our substrate overall. To attack the side opposite to that of chlorine. So when it attacks, si hydrogen, to, because it will attack, there is an inversion of configuration. So hydrogen dito, and the OH will attack there is a liquid here. So you notice the chlorine here is up, same side with CH3, no? When in the SN2 reaction, the OH will be on the opposite side, the product of the SN2 reaction, the OH will be situated in the opposite side of the CH3. So you will have, instead of cis, you will have a trans. And this is an example of an inversion of configuration. So another example of inversion of configuration is a cyclic compound. Again, this one is a trans cyclic compound, a cyclic cyclic alkyl halide or cycloalkyl halide, no? So this is your nucleophile with a lone pair and negative charge. So when it attacks your carbon here, it will attack from the back side that is opposite to that of the bromine or your leaving group. So when it attacks your I, if this is below, bromine is below the plane of this cyclic ring here, then iodine will go up. So from trans, nahimo na po siyang cis. And again, this is an example of the inversion of configuration. So in summary, for an SN2 reaction, there is a backside attack, okay, to form your product, and there is a complete inversion of configuration. Once say inversion of configuration, kung imong starting material is R, thus the product would have a configuration of S. Kung starting material would have a geometry of trans, the product will be cis, or if it's cis, the product will be trans. And in the SN2 reaction, there is only one transition state involved. So you only have one uphill climb for your product to form your reactant. So your reactant, or rather your product, can be energenic, or the reaction can be energenic, can be exergenic. Okay, so pag exergenic, the free energy is lower than the free energy of the product is much lower than the free energy of the reactant. If endogenic, the free energy na diri siya dapit, no, withdraw na siya diri dapit niya, ubos ni siya. Okay? Kung positive ang imuhang delta G. Pag negative imong delta G, you expect ni inani ubos ang imuhang free energy sa product kaysa sa free energy sa reactant. This is the reaction coordinate. Reactants, transition state, product. Okay? In the SN2 reaction, we only form one transition state. So isa ra ka uphill nga climb. So we'll see later unsa itsura sa energy diagram, no? So reaction for another kind of substitution reaction. Okay, so that will be for chapter. I'm going to discuss balik here. Okay, so we'll go to part 2. So there is another kind of substitution reaction. An example is the reaction of tert-butyl chloride and water. So then we can to ask, asa man ang atong substrate ani, asa man ang atong nucleophile. So which one do you think is our nucleophile here? Anyone? Shaira? Asa atong nucleophile ani for this example? The tert-butyl chloride and water. Which is our nucleophile here, Shaira? Are you with me? Are you listening?
Kanang H2O, ma'am.
Okay, or H2O. Anong nucleophile siya, Shaira? Because? Anong nucleophile si H2O?
Ano man, naman siya oxygen, which is group 7. Na
Huh? Oxygen is not group 7.
Sir, katong ano ma'am, kanang mag-follow siya octet rule, ma'am.
Nganong nucleophile si H2O, Gwen? Ingon si Shaira, nucleophile daw si H2O. Nganong nucleophile man si H2O? Gwen, are you listening? Gwen, natulog si Gwen?
Ay kanang kay ang oxygen man ma'am kay pwede i-donate para maka-form og bond ay amot ni.
Kasi pwede donate. Ano sa'yo definition nato sa nucleophile gani? Nika. Sa gani ng nucleophile Nika? Nika, are you listening? Nika. O si Tom Jerick. Tom Jerick. Tom, na-enroll na ni si Tom Jerick? Na-enroll na ka,
Hello,
Tom?
ma'am.
Na-enroll na ba ka?
Ano, ma'am? Yes, ma'am na.
Naka-add na ka ani nga course?
Yes, ma'am na.
So my question kay ingon si Kuan, Shaira ganina nga si H2O daw ang nucleophile ani. Okay? And so tigingon ni Gwen ka ganina. Di man nga nung H2O kay moa daw si oxygen. Unsa di definition nato sa nucleophile, Tom?
Donates electron pair
That
to
the
form a bond.
nucleophile is the one that contains an electron pair, okay, that donates electron. Asa man siya mag-donate sa electron? Paingon sa kinsa yung tagaan sa yung electron?
Ano, yun?
Kinsa may tangan? Ato siya maghatag sa iyang electron sa any positive center, like carbon, nga positively charged carbon. Okay, so akong pangutana otro Shaira, ingon si Tom nga mag-donate daw og electron pair. So asa man ang electron pair ni H2O dira na adi ay? Shaira? Shaira, makita ninyo ang electron pair ni H2O?
Ma'am.
Makita ninyo ang electron pair ni H2O? Aba,
Wala,
electron
ma'am.
pair sa H2O na wala. Ingon si Tom nga ang nucleophile daw by definition is the substance or a species that contains an electron pair that donates its electron paingon sa dapat paingon sa positive center. Ini positive center saba lagi. So my question is, Nika na pod. Nika, can you see any electron pair kang water? Nika. Okay, si Ronald. Ronald. Si water ba na ay electron pair sa H2O dire? Ronald.
Yes, ma'am. Wala.
Naawala. Sige, ayaw naman tanawa si water din ha. Sa imo na lang imagination. Si H2O ba na ay electron pair? Naa ba? Naawala. Ha?
Na.
Naa? Naa. Okay, wala lang gipakita pero naa siya. Okay? Ito ko example ko ganina. Ara si water, no? Maski pag i-shortcut siya pagkasulat, water always has an electron pair, no? Nitrogen, oxygen. So you always have to remember that nucleophiles are species, reagents that has an electron pair. So because na siya electron pair, si nucleophile is also considered as a Lewis base, sabat sa mga manok. Okay, so maski pagkasulat diri kay wala siya kanata. Oh, nato diri. So maski pa pagkasulat, okay, shortcut nga pagkasulat, you always have to think, no, kung wala gibutangan og electron pair, drawingin ninyo og electron pair para to remind you that there is always an electron pair here. Also for chlorine, no, napo na siya electron pair 2, 4, 6, 8 plus the bond to follow the octet 2, 4, 6, 2, 4 plus 2 bonds with hydrogen follows the octet. Okay. So this is our nucleophile and this is our substrate. And what is our living group? Nika. What is our living group, Nika? Natulog si Nika? Nika. Ronel. What about Ronel? What is our living group here?
And third butyl chloride, ma'am.
Third butyl chloride is our substrate. What is
Ay,
our
living group, ma'am.
Yes, the living group.
Chlorine, ma'am.
Okay, chlorine is our
Water. Ay.
Sakto na to. Chlorine is our living group. Sa ng living group kanang mubiya, kinsa may mubiya sa ila dinha, no? Si chlorine kanang nibiya nga species. So the living group is chlorine. Dili si water. Unsa ganyan si water? Bago ta nag-define, si water is our unsa si water, Ronel?
Nucleophile, ma'am.
Si water is our nucleophile. Nganong nucleophile si water, Ronel? Because
Kuan mo kaning more electronegative siya kay mo donate siya kuan electron pair.
unsa definition nato sa nucleophile? Nucleophile is a Lewis base. Nucleophile is a nucleophile is a Lewis base. What's a Lewis base? The one that contains an electron pair. Okay? So it doesn't matter kung sa gingon more electronegative. It doesn't matter kung electronegative siya or dili. For as long as na siya electron pair, okay, it is considered a nucleophile. Okay?
Yes, ma'am.
A nucleophile is a Lewis base that donates an electron. Okay? And the leaving group is the one that leaves or takes the pair of electrons with it when it leaves from the substrate. So we'll go back to our action here with third butyl chloride and water. And here is our nucleophile to form your H2O. Ano na OH naman ni siya? Yun sa kanya pag OH. And then Cl will leave. So we'll go into the mechanism later. No? How it should be COH with another hydrogen here to form your positive. Pero nga na OH ni siya. So we'll go into the mechanism because H2O will also, or chloride that is being liberated from the substrate, also attack the hydrogen from here. So let's go into the mechanism for this. So in this reaction, they found out that whether the reaction was run at a normal neutral pH or whether the reaction is run at a high hydroxide concentration or a higher or a lower but higher pH rather. So the rate of the reaction is still the same. So so therefore it suggests that neither water nor hydroxide are involved in the rate determining step. So it's not water, it's not hydroxide. So kinsa ra day mag-matter. So regardless kung mo nila ang reaction at a low pH, a high pH, neutral pH, no, it doesn't affect on the rate of the reaction. So si water walay effect sa rate of the reaction even kung ma-change ang pH of the solution here. It doesn't affect on the rate of the reaction. So sa ilang ikastorya, therefore we can say that for this kind of reaction, because of this observation that water doesn't affect on the rate of the reaction is or just simply dependent on the steric butyl chloride. And therefore the reaction is first order overall. So in this kind of reaction, the rate is dependent only on this substrate and not on the water, our nucleophile. And because of that, because there is only one, the reaction is first order. It's only dependent on one species. Okay, you only have this one. The rate is dependent on the concentration only of the substrate. In this case, this is steric butyl chloride. And since there's only one species involved to form the product, so the reaction is we call as unimolecular or first order. So you have one, and since this is a substitution, the chlorine is displaced by OH from water. So this substitution nucleophilic because here it's a nucleophile and unimolecular. And so in short, we call this as an SN1 reaction. So if you remember on the SN2, both the substrate and the nucleophile would affect on the rate of the reaction. But in the SN1 reaction, there's only one species or reagent that affects the rate of the reaction. And in this case, it is only the substrate. So this is an SN1 kind of reaction. So in some cases, there are several multi-step reactions to form on our product. Here, so for example, here you have a sand with so many different kaning mga neck, no, of the glass. So even if the second and the third neck, you can see here, kay dagko siya, but if the first neck here, there is a narrow opening, so it will affect on the flow of the sand paingon diri sa ubos, no. And since this one affects on the overflow of the sand paingon diri transfer diri sa another system here, therefore this one is the determining step, no, for the flow of the sand to the side here. So sometimes when we have a multi-step reaction, for example, you have a reactant to form the intermediate first one, and if this is the slow one, even if the formation of the intermediate 1 to intermediate 2 before you form the product, no, this is what we call as a multi-step reaction. Whatever step that is slow is the one that will determine on the rate of the reaction. So again, if you have a reactant, before it forms the product, it's first formed into intermediate 1 and intermediate 1 into intermediate 2. And in the formation of the reactant to intermediate 1, it's very slow. Even if the formation of intermediate 1 to 2 and 2 to product is very fast, then the reaction between reactant to the intermediate 1 is slow. This is the one that determines the rate of the reaction, and therefore we call this one to be a rate determining step. So step 1 in this case will become our rate determining step, even if the other step reactions are fast. So in this case, you will have 3 steps, no? 3 step reactions before you form your product. First reaction of reactant to intermediate 1, intermediate 1 to intermediate 2, second reaction, intermediate 2 to intermediate 3, third step reaction. And the overall reaction, of course, is simply the reactant to product. And these are just your intermediate step reaction. So if reaction takes place in a series of steps, again, the slow step is the rate determining step, or the rate limiting reaction, rate limiting step. So what is the mechanism for the SN1 reaction? So again, let's consider third butyl chloride here, and our nucleophile is water to form your third butyl methanol. And hydronium ion, of course, is Cl here. So let's see how does it go. So the first step is a slow step wherein the chlorine or leaving group leave first to form a carbocation. And so you liberate the Cl. So this one is aided by the polar solvent. So a chlorine departs, so our solvent here is water. It departs first with the electron pair bonded to the carbon, So once your chlorine leaves from your substrate, because it will carry the lone pair with it to chlorine, mahitabo si carbon will become passively charged. So this is a step wherein there is a formation of a carbocation. A species of carbon, when it bears a positive charge and 3 bonds only, we call this one to be a carbocation. So here is a carbocation, and your chlorine will bear negative charge. So positive, negative, of course, the net reaction, the net charge here is 0, same as on the left side. So even if you have the carbocation and negatively charged leaving group here, the net charge is still 0. So this is the first step of the mechanism for the SN1 reaction. So first is the reactant, and you form the first transition state. Here we call this carbocation to be a transition state 1. Okay, so once you form your carbocation, go for the second step. We use the nucleophile. So the nucleophile again is a species that contains an electron pair. So our nucleophile can be negatively charged or neutral. So in this case, since we have water has an electron pair here. Okay, so we will use this one, the electron pair, to donate electrons to our positive center. What is our positive center? In this case, the carbon is not partially positive, but it is fully positive. This is our carbocation. So the lone pair attacks the positively charged carbocation here. So you see the arrow here, from the electrons paingon kang carbon. So since we use the electron pair from oxygen to form the carbon, the arrow, okay, follow na nato, we form a bond between carbon and oxygen, okay? So mawala na yung lone pair because we use the lone pair pink here to form a bond, and then we have only one lone pair, and of course hydrogen and hydrogen. And then we check on the formal charge of oxygen. Oxygen is group 6, okay, group 6. So the valence is 6. Minus 3 bonds, so 6 minus 3, that's 3, minus number of unshared electrons, so 3 minus 2, that's 1 or positive 1. So the formal charge of oxygen is positive 1. 3 bonds and a lone pair oxygen would have a positive charge. So you have this intermediate 1 again, intermediate 2 rather. So once you have this, you have a positive charge here. So what will happen? We use another species of our nucleophile to attack the hydrogen here. So what happens? Again, your oxygen is electronegative rather. And of course, and there is a positive charge in oxygen. So between the bonds of hydrogen and oxygen, the oxygen would have the tendency to draw the electrons in the bond paingon sa iyaha. Okay? Secondly, oxygen is an electronegative atom. So between the bonds of oxygen and hydrogen, oxygen will try to disperse the charge, positive charge nga na-develop sa iyaha. So, ang sayang gamiton, it draws the electron density. Hala, 5 minutes na lang. Ay, no, sorry. I have another meeting. It will draw the electrons paingon sa iyaha, so the oxygen will attack on this hydrogen here. Hydrogen becomes partially positive nga naman because the oxygen will draw the electrons from the bond between oxygen and hydrogen. So what H2O or water will form a bond with hydrogen. So we'll form H3O plus hydronium ions. HOHH. Here you have positive charge, and the lone pair from the oxygen and hydrogen will go to oxygen. Okay, and so you recover the 2 lone pairs here sa imong methanol and then the hydronium ions. So total net charge, positive here and positive here. Positive, positive, left and right. So we're good. And this is our third step. So here is the formation of a second transition state. And the second transition state is reacted again with the nucleophile to form our products. So first transition state, second transition state, and then your transition state 3 here. And then you have your product here. Okay, so you notice that in the step 3, no? In the step 3, you notice that in the SN1 reaction rather, there's too many curves that you will see, because we form 3 transition states before we form our product here. If you compare that one to that of the SN2 reaction, you only see one curve: reactants, transition state, or transition state, and then the product. In the SN1 reaction, you will notice that there's 3 different curves before you form your product here. Okay, and so that's the difference between SN1 and SN2 reaction. So here again, let's summarize for the mechanism of the SN2 reaction, SN1 rather reaction. The first one is the heterolytic cleavage of the leaving group. Second is the attack of the nucleophile to the carbocation. So in the step 1 reaction is the heterolytic cleavage. Heterolytic meaning it gets the leaving group gets all the lone pairs or the electron pairs in the bond with it, and it forms a carbocation. In the step 2 is the nucleophile attacking your carbocation. Okay, and the third step is your transition state 2 reacting with the nucleophile to form your product here. So what is the structure of a carbocation? So for a carbocation, okay, it only has, let's see here, 3 bonds, no, plus a positive charge. So say itsura na niya. For a carbocation, now you have to remember that this one is a tetrahedral carbon here. It utilizes the sp3 hybrid orbitals here, sp3, sp3, sp3. So unsa mahitabo, unsa na itsura niya or shape niya when carbon assumes the positive charge of carbocation. Okay, so the carbocation are trigonal planar. So it forms a bond here with sp2, sp2, and then there's a p here. The p is there is a p here. The same with the sp2 that gamit sa alkene. In the carbocation, it utilizes the sp2 hybrid orbitals. Okay, the same with the hybridization that's in the bf3. So it uses only sp2, so 1s and 2p orbitals for the sp2, 1s and 2p orbitals to form a bond with 3 hydrogens. And then there is a vacant here that's being unused. This is our vacant p orbital. So this is manani yung itsura, no? Carbon will form a bond with another carbon since you have the 3 carbons attached to your carbocation here. So you have your sp2 and sp3 from carbon here, sp2 and sp3, sp2 and sp3 here. And then the blue one that lies up and below your sp2 orbitals of the carbon is the vacant rather p orbitals. If we are dealing with double bonds, no, this will be used to form a pi bond kung naisilingan, no? But since there is no double bond here, the p orbital here is vacant. There is no electron involved. There is no electron that occupies on the p orbital. So the p orbitals in the structure of the carbocations, it's actually vacant. Again, so you have 6 electrons here and a vacant p orbitals. 6 electrons forming a bond with another atom, in this case carbon, carbon, carbon. So there is a relative stability actually for carbocations. Okay, 6 na. And the stability is that 3 degrees greater than 2 degrees and 1 degree and then 1 methyl degree. So why is that? No, so for a 3 degree carbocation, it's much more stable. Why man? So when carbon develops a positive charge, okay, this species would try to stabilize or disperse the positive charge that's being developed in carbon. So how can it be stabilized? It can be stabilized by the alkyl group attached to this carbon. So the alkyl groups would undergo hyperconjugation. So it's electron delocalization via the partial orbital overlap from a field bonding orbital here, okay, to the adjacent here, p orbital, adjacent unfilled p orbital here. So remember here, let's see, you have your here sp3. There is a carbon, hydrogen, hydrogen here. There's an sp3, so tetrahedral structure. So 109.5, 109.5, wala na klaro. Dapat makita siya. Mura siya parallel, dili po siya in anika, vertical, no? Siya vertical, but slightly, yan siya on side, no? 109.5. So it will donate somehow the electrons, the alkyl group would somehow donate electrons from here, sp3 hydrogen electrons here to stabilize this one. That is what we call as hyperconjugation. Nanara. So you have your sp3 carbon here, sp3, sp3, sp3 carbon bonded to hydrogen. Kani siya? Ano to? Kani. sp3 carbon bonded to hydrogen, 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 tulok hydrogen. Kani, no? Okay, sp3, sp3, sp3. So there are 1, 2, 3, 4 bonds, no? So 4 bonds carbon, it assumes the tetrahedral structure. And carbon utilizes the sp3 hybrid orbitals. And sa bond angle niya is 109.5 degrees. So there is an electron between carbon and hydrogen, a bond. There is an electron. So when you have a vacant p orbital from the carbocation here, vacant siya, no? Somehow the sp3 carbon here would tend to disperse the positive charge by hyperconjugation. So the electron density from the carbon-hydrogen bonds of the methyl, getting methyl CH3, no, would flow into the p orbital of the carbocation because of the orbitals can partially overlap. So if you remember, kung parallel lang niya siya nga p orbitals, mag-overlap siya to form a pi bond. But we don't have another p orbital on the adjacent carbon. But instead, we have an sp3. Dili siya in ka perfectly parallel, but somehow mura siya slightly parallel per close, no? So it will somehow try to overlap para ma-stabilize ng passive charge carbon here. And that is what we call as hyperconjugation. Anytime a charge can be dispersed or delocalized by hyperconjugation, or what we call sometimes as inductive effects, resonance, and a system will be stabilized. So there is different ways to stabilize a positive carbon. One is hyperconjugation, another is inductive effects, another is resonance, which we will discuss later. So the system will be stabilized. In this case, what stabilizes the carbocation is hyperconjugation. Whenever you have a sp3 orbital adjacent to your carbocation, it will be stabilized by hyperconjugation. Giun sa pagkahitabo ng hyperconjugation, there is an orbital overlap between sp3 and the vacant p orbital. The same way that you can imagine how the pp orbital overlap to form a pi bond, no, when there is electron. In similar way, that's also how the hyperconjugation occurs. sp3 kanisha and the p orbital overlap sideways to stabilize this one, and that is how the hyperconjugation is being made in the carbocation or hyperconjugation. That's how hyperconjugation stabilizes your carbocation. So whenever you have a large number of alkyl groups, okay, the more alkyl groups you have, the more sp3 orbitals will be able to stabilize your positively charged carbon here via hyperconjugation. Okay, so that's why the more alkyl groups that would stabilize your carbocation, the more it will become stable. So the methyl will be the least stable one because there is no, you only have sp2s, wala na kay sp3 carbon here that would stabilize via hyperconjugation. Nasabtan ba ko? Okay, here. So here is an example. So another way again of dispersing or stabilizing a positive charge, like a carbocation, aside from hyperconjugation, can also have conductive effect. So here you have a conductive effect here. Okay, here you will have stabilization via the CH3. CH3 here is more stable than here. CH3, CH2 than here. So aside from hyperconjugation, we also have the inductive effect, electron donating inductive effect that can be made via the alkyl group here. Some inductive effect, because you have an electron density from this H3 here, it can induce somehow its electron coming from here, these groups here, paingon kang carbon. So hyperconjugation and inductive effect can stabilize the developing positive charge in carbon or the positively charged carbon atom. So again, the trend is if you have a 3-degree carbocation, then a 2-degree carbocation, and 1-degree and a methyl, the relative stability will be higher for a 3-degree carbocation. Okay, so you can click on the video for that if you want to click. And so we can, before we end, can you rank on the following carbocations in order of increasing stability? Anyone? Aisa? Aisa?
Yes, ma'am.
Which one is the most stable? ABC. Carbocation here.
A, ma'am.
A? Why A? Diba ang stability is
Ayan, letter B, ma'am. Then, ang C yun.
B. What is the degree of the carbocation here? It's a 1, 2, 3-degree carbocation. So the most stable carbocation is B. Sunod, say sunod, Camille.
Letter C.
Letter C, sunod. Sunod, Mary Japer. B, C, sunod.
A, ma'am.
Okay, wala lang choice. No? So you have a 3-degree, the most stable carbocation. Next is C, 2nd-degree carbocation, and the last one is one, 3. Of course, you have the most stable B, sunod C, sunod A diamond. Okay. Same thing with this practice 6.7. So they still have time. Do you have class? If you have class, you can go. If you don't have class, let's continue. We can continue with the stereochemistry, okay? Because for the SN2, we've learned that there is always a backside attack, no? And there is inversion of configuration. For the SN1 reaction, what happens is, since there is a formation of a carbocation, then our nucleophile can attack actually on the front, katong same side same side with our living group or likod sa imong living group. Now, anyway, it doesn't matter when we have a carbocation because first, the living group lives first in the substrate from our carbocation. That's when our nucleophile attacks. So the nucleophile attacks when there is already a carbocation. So it doesn't matter the carbocation, the nucleophile will attack front side or back side. And because of that, there's two types of configuration that's being produced. No? So, and sometimes what we produce actually is racemar. Okay, there is racemization and some non-racemization. So we can convert the reaction whenever the reaction causes chiral molecules to be converted to a chiral intermediate. Yeah, chiral. You have two types of configurations being involved. So for example, here, in an SN1 reaction of tert butyl and some 3-bromo-3-methylhexane, in the presence of water. So our nucleophile is water. What happens in this kind of reaction is that there is racemization. We were able to produce two types of configuration, the S and R configuration. So when there is a 50-50% racemic form, okay, what happens is that our product becomes optically inactive. So even if this S chiral molecule can rotate the plane polarized light and also the R, but when they are present in equal amount, so ma-cancel ang rotation of the plane polarized light. And what we have is a racemic mixture. A racemic mixture is a 50-50% S configuration and R configuration of a species. Okay, so in the SN1 reaction, there is racemization. So if the original compound loses all its activity, we call it one as a complete racemization. If the original compound loses only partially for its optical activity, we call it partial racemization. So it's called racemization. But when you get 50-50% of the product from the original configuration, this is what you call as partial racemization. But when you have 50-50% configuration, two configurations of the product, we form actually a racemic mixture. So again, in the SN1 reaction, proceeds through a formation of an intermediate carbocation, and the carbocation, because it's trigonal planar, it is a chiral. So that's a chiral. This one is a chiral. And we produce, when it reacts with water, it reacts to form two enantiomers, the S and R enantiomers in equal amounts. Again, when it's in equal amounts, we call that one as a racemic mixture. So how does it happen? We still have time. We have 5 minutes. So if you have a reaction again, it's sending up 3-bromo-3-methylhexane, optically active. This is in the S configuration. So when it forms the product, there is S configuration of the product, but there is also R. So there is a partial racemization here. So what happens, of course, is the same as we did in the first one. The first step for the reaction is the formation of a carbocation. So there is the living group leaves first to form your carbocation. So the living group gets with it the lone pair for the electron pair. So you have Br ko. Kulangan niya siya. There should be another one here, another dot here. So if there should be another dot to be negatively charged. Again, becomes positively charged. Since you have a carbocation, your nucleophile can attack up and below, or front and back, or up and below to the plane of your carbocation. So when it attacks, like here front, you have this configuration. When it attacks sa ilalom or sa ibabaw ni, when it attacks sa step 2, when it attacks sa ibabaw, okay, you get this product. When it attacks sa likod, sa ilalom, you get this product. So both of the products would have different configuration. And when they are present in equal amounts, you call that one a racemic mixture. So even if the individual S product and R, or is it the S or the R? So either way, even if they are optically active, as you've learned in the stereochemistry class, If they are present in equal amount, makancel ang rotation of the plane polarized light, and therefore the mixture, the solution becomes optically inactive. Even if this structure or this structure is optically active, but since they are present in equal amounts, they both cancel the rotation of the plane polarized light, therefore it becomes optically inactive. Okay, mara to. And we'll continue. So many keeping in mind that the carbocation, what's the question? Write structure for the carbocation intermediate and write the structure for the alcohol that you would expect from reaction of SN1. Okay, so this will be the problem set. And then we'll continue with the lesson. So that is for the SN1 reactions, the mechanism for the SN1 reaction. And next meeting, we'll compare on the SN1 and the SN2 reaction. So what are the factors that affects the SN1 and the SN2 reaction? Okay, and before that, there's also what we call a solubility reactions. Usually we do the SN1 reaction, whatever our solvent is also our nucleophile. Usually in the SN1 reaction, kung unsang solvent, maupod ang nucleophile. Whenever you have the solvent to be the nucleophile, you call that one to be a solubility reaction. Example is the one that we showed earlier. The water is our nucleophile and water also is our solvent. So when you have that kind of reaction, you call that one as solubility reaction. It's still a nucleophilic substitution, and the nucleophile is the solvent. So if water is your solvent, water becomes your nucleophile, it is a solubility reaction. If methanol is your nucleophile and still methanol is your solvent, again, it becomes a solubility reaction. Okay, so problem 6.5, problem set, problem 6.8, 6.5. This is a problem solved reaction. It's a question. What product would you expect from the solubility of this one? It's H2OH. Of course, here you have eggshell here. So since we form a carbocation, your CH3O, CH3, the H will be removed later, no? Will form, there is a likod or there is a front. So there's actually two products being formed here. Okay, so there is a up or there is ang dapita. It's either way, get your product for SN1 reaction. Okay, so next meeting we'll compare on the SN2 and the SN1 reaction. So you can eliminate, for example, you have systems and you can predict what kind of reaction will the given set of reactants and conditions would utilize, no? Or what type of nucleophilic substitution given the conditions of the reaction system. Okay, so up there. That's all for today. Have you learned something? Do you have questions? Do you have questions? And please log into your LMS account and indicate your attendance. Attendance will go to participation. Yes. Okay. So see you next meeting Friday.
Ma'am, close na ang attendance, ma'am.
Ha?
5 p.m. rush pa, ma'am.
Ay, 5. Di ako nabutang. But it's 7. Hmm. Anyway, so your review, I have also uploaded. Naka-record ako. Hopefully naka-record ko, no? Naka-record ko. Don't tell me wala. Naka-record ko. So, kinsa may absent? Actually, for me, wala ko pakialam sa absent. For as long as you submit your problem sets, you make up for the lost time, it's fine. 131. Not sure. So, wala lagi ang 131 dali. Ano wala? Where is the 131 here? Wala siya. Di ba naka-receive man mo og kuan ako message, di ba? Ganitong bikon. Anyway, so later na lang. Okay, picture na lang. I'm gonna wait. Can you please show your face? Screenshot for the attendance so I can remember for the next meeting. One, two, three, print screen. Okay, that's all. See you next meeting. Okay, so see you next meeting. And I will post the problem set also for the quiz. The quiz will be your exam from previous meeting, previous course, no, 130. That's all for today, and we're already having an overtime. See you next meeting. If you have no questions, you can leave the chat. You can leave this Zoom.
Bye, ma'am. Thank you.
Mm-mm.